All right, so we're looking at calculating the electric field from the electric potential today. And the objectives on that are A dot 2 dot B 3 and 8. So understanding electric potential so you can determine the direction and approximate magnitude of the electric field at various positions given a sketch of equipotentials. And the one that's a little bit more focused on today is the general relationship between the field and potential and defining and applying the concept of a conservative electric field. All right. So here we go. So we remember that we can calculate the potential from, if we know the electric field, we know how to get the potential. We had to integrate, right? We found that delta V is equal to, the delta V is the negative of the integral of the electric field dotted with the path ds or dr. All right, but from that, so from that we can, well, we figured out how to calculate the potential if we know the electric field. That means we can also calculate the electric field if we know the potential, right? And what would we have to do in order to go backwards there? If we know the electric field and we want, or if we know the potential and we want the field, what's the mathematical technique that we need to use? Or what's the inverse of an integral?
Derivative.
Yeah, we would take the derivative. So since we have to take the integral of the electric field to get the potential, we know that we can get the electric field by taking the derivative of the potential. And we go component by component usually. So the x component of the electric field is going to be, and we'd have to remember the negative sign, is going to be the derivative of the potential with respect to x. And also, if we want the y component of the electric field, we would take the derivative of the potential with respect to y. Right? And you probably, I don't know if you do partial derivatives in AB or in BC. Do you? Have you seen the
Do what?
partial derivatives?
Partial derivatives? I don't think I've seen that. I did AB last year and I don't remember it. I mean, it was like 8 months ago or something now, so like I couldn't 100% be wrong, but.
Okay, so very quick partial derivatives. It's basically saying that if we take the derivative with respect to x, that we would assume that the y is, any y in the expression is just constant. We would treat it like any other constant. And if you're taking the partial with respect to y, then you would assume x is a constant and you would treat that like any other constant. So for example, if I have f of x is or f of x and y is 3xy squared. The partial derivative with respect to x. Anybody see what that's going to be? So in that case, you would treat, since we're taking the derivative with respect to x, we would assume every other quantity is a constant.
Oh, so one of them would be dy over shit.
Well, so just with respect to x, right? We have 3 times
x would be it would be 3 times 2y dy dx.
So that would be that would be how we would go for the total derivative. But with the partial, we can assume that y is going to be constant. So the partial with respect to x is just 3y squared.
Oh.
Right? If y squared is a constant, or if y is a constant here, y squared is a constant, and the partial with respect to x would just be 3y squared. But if we did the partial derivative of x with respect to y, then we would treat x as a constant. And what would we get if we took that derivative? it's a constant times y squared. Well, we know the derivative of y squared is just 2y. So multiplied by the constant that we have out there, we get 6xy. Okay. So when you're taking a partial derivative, right, you just take a derivative with respect to this variable, and the other variable you assume is constant. So since we were taking it with respect to x here, we assumed y was constant. So 3y squared times x just gives us 3y squared. And in this one here, we assume x is constant because we're taking with respect to y. And then we get 3x times 2y, which is 6x. So that's what we mean by partial derivatives. It's really no different than doing regular derivatives, except one of the variables of the function is going to be constant, treated as a constant. And we'll see more then as we go. The problems tonight have some quick calculations of, or one of the problems tonight has a quick calculation of the partial derivative. But if you can do regular derivatives, you can do partial derivatives. So in vector so in vector notation, we can write these to as separate equations, but in vector notation, we can write them kind of together as one vector equation using a function, using what's known as the gradient. And the symbol for the gradient is negative, or the symbol for the gradient is this upside down triangle. This means gradient of the potential. So the electric field is the negative of the gradient of the potential, and we define the gradient as I hat times the partial derivative with respect to x plus j hat times the partial derivative with respect to y. And that matches up what we got here, right? The x component, or the I hat component, is the partial derivative of the potential with respect to x. The y hat component is the partial derivative with respect to y. For now, or if you're a little confused by the gradient, you can ignore we'll just look at one dimension for a while. So you can basically ignore the stuff about the y and just treat this as a normal derivative with respect to x. So, so if we graph, and we're gonna look at more, the best way to understand the relationship between potential and electric field is by usually visually with a graph. So in a graph of v versus x, what is the slope going to give us here? Remembering that the slope of a graph in calculus terms is the derivative.
Derivative of the tangent line, correct?
Derivative of the tangent line, no. Well, the derivative will give you the tangent line, right?
Yeah.
So yeah, the slope gives us the net. Well, since it's the negative, the slope gives us the negative of the electric field. Of the x, really it's the x component.
Mr. What's that word after so in
Oh, graph. That's a graph.
Okay.
Yeah.
No worries.
Okay, so let's make a couple of graphs of some simple potentials here. So first, a constant electric field. What would the electric potential look like for a constant electric field? Let's say to the right. We want a slope that's constant n, right? And if we want to say that the electric field points to the right, then our slope should be negative. So a function that gives us a negative constant slope would be a line, any line that slopes down. Right. So if this is our potential as a function of x, this gives us a constant electric field, right? Because the slope is constant, right? Wherever we look. If we want to look next at the potential from a point charge, right? When we're near a point charge, well, we know that the potential from a point charge looks like 1 over r, right? So it's going to look something like this. And we can see here that here we have a large electric field, right? Because we have a big slope. And here we have a smaller electric field. Because we have a smaller slope. So if we have a map or a graph of the electric potential, you can figure out, you know what the field is because it's the slope. And that's the same, well, and one more then, and then I'm going to compare it to gravity. That's a little easier thing to visualize in your mind. Another thing we could have would be a constant potential. Right, so a constant potential like this, what would the electric field be from a constant potential?
Uniform.
It would be, yeah, you can go even farther though, right? Not just uniform. This is a constant or uniform electric field, right? Because the slope's the same everywhere.
Wouldn't it just be constant?
It is going to be constant, but can we also say the value of it? Of the electric field? Because specifically, what is the slope along here?
Infinity?
Oh, 0.
0, right?
Oh, 0, 0.
Yeah. Right, because horizontal, right? So the slope is just 0 everywhere on this line, right? So anytime you have a constant potential, the electric field is 0, right? And that's an important kind of equivalence to understand. If the potential is constant, then there's no electric field. If there's no electric field, then the potential is constant, right? Because if the potential is not changing, then it doesn't take any work to move a charge from one place to another. If the potential is the same, so there's no electric force that you have to overcome or have help. To think about it in terms of if we, in gravitational field and gravitational force is the same thing. What's the remind me of what the gravitational potential energy is near the surface of the Earth. We know that, right? And what?
Potential energy. Well, that's just your mass times at g, right? Mg squared.
Not mg squared. You're close. There's another. What does it depend on? Your potential energy when you're the Earth.
MGH.
MGH.
Height.
Thank you, Michael.
Right. So the height. But then we know what the acceleration due to, or the force, right? The force due to gravity is near the surface of the Earth.
Mg.
Right? So if we call this, if we graph that, right, here's our height, or sorry, here's our, we'll call it our height. Here's our potential energy, right? MGH, right? This is just a constant times height, so it's a straight line going upwards. If we take the derivative of MGH with respect to h, we just get mg, so that's going to be the slope of this at any point. All right, so just like the gravitational force is the derivative of the gravitational potential energy, we also have the electric force as the derivative of electric potential energy, which is the same as saying the electric field is the derivative of the electric potential. The only difference between the gravity example and the electricity example of a constant E field is that the electric field is the negative of the electric potential, the minus sign. All right, so we'll look at this some more. I'm not sure how well this one went. But are there any, this is the end of the lecture for today, but are there any questions or anything you want to have cleared up or dig deeper?
It all makes sense now, but I think once like we see the problems, it's gonna be when we're gonna have more questions.
Yeah, I think so too. And the three problems that I've assigned for you tonight, there are the first couple of them, you're looking at graphs of potential, right? And you have to figure out what the electric field is just from the graphs. And if you know the electric field is the negative of the slope of the potential, that's how you do those two. And the third one, you'll actually be calculating a couple of the derivatives. But they're all pretty straightforward. So if you can do that, you should be okay with those. But feel free to send me an email or ask for any kind of help you need. And the other thing we're going to do is do more with visualizations. It's kind of easier. It's easier to see in one dimension, but of course our potentials are in reality, and they're in 3 dimensions, right? But we'll see how to look at 2-dimensional maps of electric potentials and electric fields and see how they're related. But if you can kind of remember that the potential is kind of like the height in gravity, or the gravitational potential energy, and then the electric field is the slope. So how steep, the steeper just like with gravity, the steeper the hill, the larger the force is going to pull you down the hill. Well, same thing here with potential. The steeper the potential hill, the larger the electric force is going to be. And I'll try to see what we can do to make that a little bit